about whether or not we saw activity with the grooves on Phobos. So my understanding is that we actually do see landslides on some grooves in MRO images. However, as far as I know, we haven't seen any changes in them in subsequent images, either on MRO or Mars Express. So that's, but Jim, I'm sure you've seen stuff.
In the PSS special issue on Phobos, there's a paper by Vasilevsky et al. which treats a lot of the geological features such as this, and these landslides are obvious in some of the craters. They're not really like the kind of thing you'd be dodging kind of thing, but they're relict. And so we've looked at a lot of the data and haven't seen much evidence for very recent kinds of things, but we haven't actually addressed the question you raised, which is, comparing the images from one period of time to the other. The Viking images, of course, aren't as high resolution, but still, it's something that needs to be done. That's a good point.
And just to complete what Jim added, we of course see plenty of chutes landslide on Phobos. Your question was specifically about the grooves, whether or not we saw any sign of activity within the grooves. So my comment was about landslides within grooves. So we see landslides within grooves in MRO images, but there's not enough repeat to see any change so far. Okay. But I have a question for Mihaly, I think. So Mihaly, on the trailing side of Phobos, where the dust from Deimos is coming in, what's a typical impact velocity of the dust?
My recollection is about half a kilometer per sec, 500 meters per sec or so.
Okay,
maybe less.
So it could do some micrometeoritic gardening.
It could do some gardening. It's in the data files. I have to look it up.
Yeah. Okay, that's interesting.
I have questions for the last two presenters. The question about can mass spectroscopy resolve the isotopes? Can it measure isotopic composition of neons and argons? That's the first question. The second question is, it might be later. We can talk that, and then maybe second.
I haven't looked in particular at argon or neon, but in the mass spectra that I show, you definitely can see, for example, magnesium isotopes, silicon isotopes, and mass spectrometers are definitely sensitive enough to separate them out. The problem is that they typically have order of magnitude smaller, depending on the element, they typically have, significantly smaller peaks. But that is something that if you're trying to do these types of detections, you would need to account for how much of, for example, iron 55 versus 56 do you have. So you should take that into account. Mass specs can see it, though.
Yeah, and the second question is about nitrogen. I just was wondering, I saw here distribution of elemental distribution, and nitrogen is not there. Why?
Not being a surface composition expert, all I can say is that we took an analog from, I think it was a D-type asteroid, and those were the dominant 6 species. The model is capable of running whichever species you may wish to study, but I don't typically know that nitrogen's a real dominant one.
Yeah, nitrogen, it's a very volatile molecule, and so you wouldn't expect it to stick around. It's just going to desorb. It's going to leave.
Yeah, if it basically combines with CN, let's say, then it can be much less volatile. And the point is that it looks like all the planets that we know, the Earth, Venus, it's has nitrogen-rich atmospheres, and probably Mars also has nitrogen-rich atmospheres. So we expect some contamination, during the history, the first at least few 100 million years. Contamination of the Phobos' surface. I have a poster here. Talks about it by nitrogen. So nitrogen, and especially nitrogen 14 to nitrogen 15, it's one of the critical ratios that will tell us about actual life.
I can tell you that we have recent observations at the moon of nitrogen and oxygen flowing out from the moon, from Earth and impacting the moon. So it's possible that something similar happens at Phobos and Deimos. Also, not being a Mars atmosphere expert, I don't know how much present-day nitrogen is in the atmosphere of Mars, but I don't think it's much.
Yeah, you're absolutely right. I mean, the lunar measurements show the presence of nitrogen in the lunar soil, but because Phobos spent, the over 80% in the magnetotail of Mars, so and it's much closer by a factor of 20 compared to the Moon. The contamination should be much greater, orders of magnitude.
Yeah, we should get a Phobos sample.
My question was, if I remember correctly, the reason we believe that Phobos' original orientation was the reverse of what it is now is because the trailing edge seems to have more regolith than the leading edge. If the Deimos deposits dust on the trailing edge, could that mean that Phobos' original orientation is the same as its current orientation?
I have to think about it. I don't have an answer.
I would like to go back to the mechanical properties of Phobos, the bug Phobos. So it has been proposed that the upper layer could be more rigid than the interior. And for me, this is very surprising because the regolith is known to be particularly cohesionless, and even radar measurements from the surface have shown that the regolith at the surface of Phobos could have something like 30% of porosity. So we should expect to have a surface layer less rigid than the interior.
Well, low cohesion is not cohesionless. With rubble piles, the cohesion is mostly in the inner particle cohesion by various forces like van der Waals. And it's really a function of surface area to volume ratio. So if you have smaller particles, you change the surface area to volume ratio and you actually get more cohesion than big particles. And so it's really a function of the average particle size. And the nice thing about the surface is that you have a micrometeorite and meteorite bombardment, meteoroid bombardment system that grinds stuff up and creates more fines. And if you look at the interparticle friction on low gravity bodies, it's very difficult to actually move material into void spaces at depth. And I wrote a paper on this many years ago, and I can send you a copy. But just a simple friction versus gravity model shows that the fine stuff is really stuck on the outside where it's being generated. And so, although it's not very much cohesion, and in the immortal early words of astronauts on the moon, you can kick it around with your feet, it still probably has more bulk cohesion than the stuff on the inside, which that's where the bulk of the porosity is. So a 30% porosity is actually kind of on the low end for Phobos. And you get much more porosity on the inside and much less interparticle contact. It's really the dust and the fine stuff that holds these things together.
So, Mihaly, I was going to comment further on the accumulation of Deimos dust on the trailing side. If it turns out to be a net accumulation that's anywhere close to 100 nanometers per year, okay, that's about a meter every 10 million years. Right there, it would imply that if you want to sample something that's not coming from Deimos but from Phobos, if you're drilling only down to, let's say, a few centimeters, you would want to do that on the leading side.
I agree.
Yeah.
On the other hand, I would be very nervous if these models have to be tested before we do sample return.
Sure.
Sending people there.
Sure.
I would rather see, mission looking into these things so we can pin down these statements.
And my comment is also to make Dan come back here and fight it. But yeah, no, it's.
I'm in violent agreement.
But we do need to fold in the meteoroid bombardment and see how much redistribution you're going to get across the object and gardening. And that's way more complex than I can handle.
But where the bluer unit is seen most visibly is coincidentally and consistently, I should say, with your model is on the leading side. So.
I have a follow-up comment regarding all of this redistribution. Ken Ramsley, Brown University. As I pointed out yesterday, if you have an impact on Phobos or Deimos, and if you have any ejecta coming out of that impact, it goes back into orbit around Mars and intersects the same body on the opposite hemisphere. So if you have even an impact of 50 meters per second, most of that material is going to be ejected back into orbit around Mars and reintersect Phobos or Deimos on the opposite hemisphere. If it's 500 meters per second, that process will repeat many times. So in general, unless you're talking about very low velocities, tens of meters per second, just about any impact on these bodies will distribute globally around the entire surface of the bodies. So in terms of trying to say, okay, the flux is on one side, the deposition is going to be global. I just wanted to get that general concept out.
So you're absolutely right, but I would still argue if I add to the orbital speeds, which is 1 or 2 kilometers per sec, Phobos and Deimos around Mars, another 500 meters per sec, your semi-major axis is enormous compared to the original one. You don't recollect.
It goes back into orbit.
That's right. That's right. And then radiation pressure, other forces, has due time to distribute it. So we try to do justice when we integrated orbits. And there is an isotropy. You really, because of the orbital element distribution, you're catching up. The Deimos dust is catching up with Phobos, and that's where most of the dust will arrive from.
I'm thinking of particles.
Yeah. Sure.
Hi. Mikhail, just a point on your dust deposition model. At some point you reach an equilibrium between Phobos and Deimos because the layer becomes self-shielding. So, it sounds like a lot, a meter in 10 million years, but it's less than that, because you're just recycling stuff from both surfaces.
So that's the part I imagine one could easily handle. The part I cannot handle is the bombardment history. We have the Geminids. 100 or 200 years ago, we did not. 200 years from now, we might not have it again. So I don't quite know how the dust influx per se is coming into the Martian system. We are slowly comprehending what's happening on the Earth. Since I follow, the argument goes, the amount of dust coming in from people to do radar versus optical between 50 or 5 and 150 tons a day. So there's a lot of uncertainties. The one that is going to be, the self-limiting case, provided that the fluxes are stationary or constant in time, that we can solve. But you're right, it has to be considered.
Yeah.
It's probably obvious to everyone, but let me say it anyway, and I'm sure Andy will re-emphasize this afternoon. The trailing side, where you want the largest accumulation of particles on Phobos, is the area that we have the poorest image data currently. And so we know even less about that important trailing side than we do other areas. We'll, I'm sure, come back to this in our SKG.
Okay. So with this one, we close the session. Thanks, everyone, for talking, and see you in 10 minutes.
Can you emphasize the 10-minute break?
Yeah, okay, and we'll start again at 10:10. So be here. Thanks.